Good morning.
Good morning.
I am Robert Titus, a professor of geology for 44 years. And I did a considerable amount of serious geological research. I'm a paleontologist by training. But in the last half of my career, I gravitated towards popular science writing. And many of you probably remember Catskill Life magazine, and my wife and I had quarterly articles in that. I think we wrote 150 articles for them. We worked for the Woodstock Times. Currently, if you live in the Catskills, Johanna, my wife, and I write for the Mountain Eagle, which is a weekly paper, which I think I can claim is the newspaper of the Catskills. And unlike most local newspapers, it's doing pretty well. So if you live in the Catskills, I urge you to find some place where you can buy the Mountain Eagle and read our weekly columns, which are brilliantly written and extraordinarily interesting. But if you're here, it's the sort of thing that I think you'll find beneficial. So where are we? We're at Opus 40, and there it is. It's a quarry. It's an old bluestone quarry. It was probably here 130 years ago, turning out slabs of bluestone that were used for sidewalks and for window sills and such. And then in the 1930s, it was purchased by Harvey Fite. Harvey had been a professor of art at Bard College. He was a sculptor, and he liked to sculpt bluestone. Currently, my wife and I are working on a short series about the bluestone artists of the Catskills, and yesterday's paper had an article about Harvey Fite. Next week's newspaper will have one about Tom Gottsleben, who lived very close to here and also owned some old bluestone quarries and turned that stone into art, and pretty good art, I think I can say. My wife is a biologist, I'm a geologist. We're both scientists, but we're very interested in art, and we're participating. I think we could almost call ourselves art historians now. Well, so here we are at Harvey Fite's quarry and the work of art that he turned that quarry into. But we're going to travel back in time about 385 million years ago, when some marvelous things were happening. Something that you would identify as southwestern Europe was colliding with North America. This is Europe right here. This is North America. The collision of these two masses of crust created an uplift, a mountain range called the Acadian Mountains, and there they are. Had you been at this spot, this longitude, this latitude, this spot back then, 385 million years ago, you would stand and you would look to the east, and rising over that horizon up to about 2 hands would be the profile of a towering mountain range. What an astonishing thing it is to contemplate that. From time to time, there would be great volcanic eruptions. I always like to imagine myself at night right here looking to the east, and a volcano is erupting, and red light is glowing on the horizon and lighting up the clouds which are rising out of the eruption. And we can hear the rumble and the roar, and occasionally we can feel the earth shaking beneath our feet. It would have been thrilling, it would have been exciting, and it really did happen. This spot was here. You always have to remember, this spot was here 385 million years ago, on a July, whatever it is, the 27th or what, whatever it is. That date did pass. That date was right here. And we're going to learn about what was going on right here. The mountains rose and the crust sank, and then the mountains eroded and the sediment washed down to the west of those rising mountains and created a delta, something comparable to the delta that makes up the country of Bangladesh today. That big and that tropical, and with a great extensive foliage. And I show you a picture, and I stand before you and tell you that had you been here on that day so long ago, it would have looked like this. We have never found more than a handful of plant fossils in the quarry, but when you add them up, they give you this image, this picture. This is here 385 million years ago. Well, you look at the plants, and that's what catches your attention, but beneath those plants is earth. Sediment turning into soil, soil producing the foliage that we see in this image. We're not going to see the plants this morning, but we are going to see the sediment that lay beneath them. We're going to learn about what that sediment tells us about this particular past. Then we're going to advance through time, almost all of those 385 million years, and we're going to visit the Ice Age. And we're going to find that glaciers visited here. That's the Hudson Valley. The glacier, the last glaciation, came down the Hudson Valley, turned to the east, overran Woodstock, and reached right here. If you stand and look towards the Hudson Valley, in your mind's eye, you can create an image of a frigid landscape, and you can look in that direction, and coming towards you very slowly is a glacier. Right here, no kidding. A glacier advanced down the Hudson Valley and reached right where we are standing right now. How do I know that? In a few minutes you're going to see the evidence, and you're going to see some pretty good evidence. Let's go in this direction and start our journey.
Boulders that sort of have that.
Well, you'd have to
tell me what it is, but it just seems like it's cataclysmic volcanic activity to kind of.
You guys are so tiny.
What's obvious.
cobbles.
Yeah.
Well, these are rocks, but you probably knew that already. This is flagstone. This is what they quarried for. These slabs of rock break horizontally and can be cut up into sidewalk slabs or window lintels. And 150 years ago, this was a big industry in this vicinity. There must have been a day when there were more people working in this quarry than had ever been before or ever would be again. And they were busy. They were industrious. And they were part of the Catskills economy. Well, there's stories to be told in these rocks. Can anybody look at this rock and, having had a good earth science course somewhere along the line, tell me what you're looking at?
Striations from the glacier.
Yes, what was that word?
Striations.
Striations, all right.
Yeah.
Yes. Yes. We have a winner. Somebody had a good earth science course. Let's get at it, what I'm talking about. Look at that. This gentleman called that a striation. It's a good one. Here's another. Here's a third. Here's a fourth. Here's a fifth. A sixth. Huh. And they're all parallel. Huh. There must have been a moment in time, maybe centuries ago, when the first living, breathing human being noticed something like that. And it caught their attention, and they must have scratched their head and said, I wonder what did that. And there was no possible way of answering that question. And it would be centuries before the evidence would appear. And that was in Switzerland during the 1820s, when the Little Ice Age came to an end. The climate warmed up. This was good global warming, which made the world so much more suitable for us to live in. And in the valleys of Switzerland, rocks came to be exposed that had been under the ice for several hundred years. And when they looked at those rocks, they found these striations, these scratches, and they all pointed downhill. And they said glaciers had descended the Swiss Alps, carrying with them sand, which polished the rock, and then gravel and cobbles and boulders, which as the ice advanced, scraped across the surface and left those scratches, those striations. Evidence of what was clear to them, they lived in Switzerland, evidence of a glaciation, evidence of an ice age past. Well, people caught on to that, and they started noticing that these features could be found all around the globe if you were close enough to the pole. And it dawned upon them that, there used to be a lot of big glaciers on our planet. And they mapped the distribution of these things, and they found that all of Canada had been glaciated, and about a third of the northern part of the United States had been glaciated. What a discovery that must have been. And again, there must have been a moment in time when the first human being looked at the maps of these features and understood, comprehended how massive this glaciation had been. Well, minutes ago I showed you that map, and we saw a glacier filling the Hudson Valley, coming down the valley, turning to the southwest and overrunning this spot and keeping on its way considerably to the west.
So why aren't they
how high was
all
the-
striated?
Say again?
Why are they not all striated?
Well, this rock was exposed at the surface during the time when the glaciers advanced. These rocks were buried underneath. They were quarried and brought to the surface that way.
I see.
The thickness of that ice at this spot, what do you think it was?
No less than 4,000 feet in elevation rising above us.
Can you imagine that? That's
Yeah,
amazing.
no. Well, you don't
Almost a
have
mile
to.
thick.
You can travel to Antarctica. They have planes that fly
Sure.
people across Antarctica. You can travel to Greenland and see comparable glaciation. I bet you 3,500 feet of ice rose above us right here. Look up into the sky, 3,500 feet.
It's about the height of the mountains.
Yeah, yes, it was above. When you climb to the top of Overlook Mountain at the fire tower up there, you'll see rocks that look just like this. The glacier passed across the top of that mountain.
Yeah.
I always say, "Ha!" Well, let's keep going. Big as a house.
And this is one surface, is that right?
One surface, all around the quarry.
Yeah.
Yeah.
Wow.
Have you ever seen anything like this?
No.
No, that's the right answer. And here's the other question. Would you have even noticed it had I not brought you here and pointed? Well, we'll never know the answer to that question, will we? But now that you have a trained eye, you've been brought to a magnificent glaciated surface. It's hard to find something better than that, though they do exist. We stand here and we look in that direction, and in our mind's eye, we see a glacier advancing towards us, coming down the Hudson Valley, turning in this direction, rising higher and higher on the horizon. All around us is tundra. All around us is the desolation that comes with a very frigid, very cold climate, an ice age climate. And here is the evidence. Nobody has ever doubted the ice age theory because the evidence is so convincing. Nobody has ever come up with an alternative explanation for what you see here. And nobody has ever not been truly awed by what they see when they look at something of this sort. I'm a writer, and I try to be very careful to avoid words that are overly used. And the word awe and awesome are intensely overly used. And but I can't think of a better word that when I stand at a site like this and I conjure up an image of what the evidence tells me. This is science. This is science as good as it gets. Now, I know you all tried your best to avoid taking your science requirement. And then you meet a scientist, and he gets so excited. He gets so excited about explaining science to you. At least the ones who can get excited and can explain these things. And, well, look at this. Crack, 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 crack. And what's the striking thing about these cracks? They are all of them parallel. Now, we have something, they're parallel, which means there's a pattern to these features. When a scientist sees a pattern, that scientist knows nature is calling our attention to something that needs to be explained. And if we can explain that something, we're going to learn or discover, make a discovery that we can call science. But it's not obvious, is it? What could have possibly caused these fractures to open up and to all be parallel with each other? Well, we're going to take that up when we get to the bottom of the quarry, where we can get more evidence. Let's keep going then. Well, we've got our eyes open, and we're starting to notice things, and we're asking questions. And there's a pattern on the surface here. Something obviously occurred on this surface, and look at that. It occurred a lot. And the answer to your question is that snails did it. On very humid seasons, when it's been raining a lot, it's not unusual for snails to come out of wherever they're hiding, and they crawl out onto the surface where they find that algae have been growing because of the rainfall. There's a coating of green algae on the surface, and that's what these snails like to eat. They crawl across the surface, scouring up algae, and glug, 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 and they think algae tastes good, and it's nourishing, and they like it, and that's how these particular snails make their living. They have a rasping device next to their mouth, which they grind away at the bedrock, and they scrape away anything that would create color, and leave these patterns behind. These are going to be here. They'll be here next year or the next
Okay.
time. It'll be a long time before we get rid of them. These probably took decades to
Okay.
accumulate.
Okay.
It's the first step in science is to perceive something and ask a simple question. And you look at that and you go, huh, that's interesting. I wonder what did it. And then when you solve that question, you've answered a scientific problem, a scientific question. You're more learned than you had been a few minutes ago. Now, when you take your children and grandchildren to out for walks, I want you to watch for these things and explain them to it. Have you ever seen evidence of glaciers before?
Well, probably.
You have. Good for you. Well, most children haven't. And I can remember the first time I saw this sort of thing. And again, I think the word awe is appropriate. I was really, it caught my attention. It sure did. And I'll never forget a moment of that sort.
Great.
Again, so much of a field science. My geology is a field science. I spent plenty of time in the laboratory when I was a professional geologist, but this is what I like to do. This is where I like to be. And it's a field science dedicated to searching out and finding patterns. And here is a pattern. This is a stratum of sandstone. This is another stratum, a third, a fourth, a fifth, a sixth, a seventh, an eighth, and they're all doing the same thing. Each of these strata we have a pattern. The strata all are inclined towards the left, and this continues off into that direction. There must have been centuries ago, I would imagine, somebody who today would call himself a geologist who noticed such a thing and scratched their head and said, huh, I wonder what that is. I wonder how that happened. They could ask the question. The way somebody asked a question about the fractures up there, somebody asked a question about the snail patterns, and somebody, for the first time in the history of humanity, looked at something like that and said, I wonder how that happened. Centuries later, there was a drought somewhere, and a river dried up, and a professor of geology got his graduate students together. The 14th Amendment has done away with this sort of thing, but he commanded his graduate students to get shovels out and to dig a trench across the desiccated, the dry out river channel. And when they looked at this, they found sand that they had dug through, which was deposited in these inclined strata. and they all pointed in a downstream direction. They realized that not during a drought, but during a flood, masses of sand had been carried by a river. The water was dirty with sand floating in it, pushed down the river by the currents, the powerful currents. And then when the flood subsided and the flow slowed down, the sand dropped out and was deposited first as an inclined bed, then as a second, then a third, then a fourth. This is a flood deposit, but specifically it was deposited at the end of the flood when the flood waters were slowing down. And those poor, beefy graduate students had labored so intensely, but they had made a discovery. And a discovery which is taught to all young geologists today and is carried with them into the field. And it's a bit of knowledge that they walk up to an outcrop and point and say, river deposit downstream. Lithified sand would be a better phrase. It's hard to compress sand. It's just sturdy stuff. This was sand deposited in a river channel, which 385 million years ago has had time to harden into sandstone. Well, all of your lives, you've driven past outcroppings of rock. All of your lives, you've walked past outcroppings of rock. And I bet almost none of you have ever paused and noticed things like this. And still fewer of you were able to explain what you were looking at. My science is a science of noticing these things and explaining these things. Now, I described our region as being deposited in a great delta. I compared it to the country of Bangladesh, which is an enormous delta at the bottom of the Himalaya Mountains. I described mountains off to our east, which towered above at horizon. They may have been as tall as the Himalayas, and this may have been, probably was, a delta as big as the nation of Bangladesh. I'm telling you, the Catskill Mountains are a petrified delta. If you took Bangladesh and waited 400 million years, its sediments would harden into a petrified delta. If you then could lift Bangladesh up a couple thousand feet and then erode it and then cut quarries into it, Bangladesh would look like this. 385 million years ago, this looked like Bangladesh today. 385 million years from now, Bangladesh will look like this. That delta, the Ganges River Delta, is a twin to the Catskill Delta. The two twins are separated only by time. They're perfect twins, formed by the same geological processes. Isn't that a revelation of sorts? It's just rock. But I've conjured up an image of the nation of Bangladesh, and I showed you that picture before of the dense forest that once grew here on the Catskill Delta. I think fair to say it's a revelation. It's looking at rocks and their past is revealed to us. And the past is interesting. It's fascinating. It's so different. Let's look at some evidence.
Mississippi Delta would be different because there's no mountains near there?
There are no mountains. It's not quite as big.
Okay.
The Mississippi Delta is sediment carried by the Mississippi and Missouri rivers across the continent to get to Louisiana. So no mountains. Mountains are very helpful if you want to build a delta. Very helpful. But in that case, no.
Okay, and then there's a section here which looks more flat
Yeah,
and
down
thinner.
here.
So is that just regular like leaf sediment that compressed?
Right here?
Yeah.
Yeah. That's a different type of rock. It's not a sandstone. Good. This is an observation, you see, and you're asking the question. When you have a delta, you have rivers flowing across the delta, hundreds of rivers on a big delta. The Ganges River has scores or hundreds of, Ganges Delta has scores or hundreds of these rivers, but the Ganges Delta has a lot of other things, including swamps. What accumulates in a swamp? Not sand, but ooky, dark, carbon-rich mud. That's a swamp. It was a swamp sitting here, minding its own business, not doing nothing to nobody, when a river flowed across the top of it and deposited those sands. Swamp river.
So what's this under stuff?
Down there at the bottom?
Well, between the swamp and the ground. That
Yeah,
whole layer.
right here. Well, it's more sandstone, and it's flat-lying. It's not tilted, and that gets us back to those beefy graduate students who, in violation of the 14th Amendment, were ordered to work without pay digging across that river channel, where they found inclined strata and they found flat-lying strata. These are the flat-lying strata of the same river. Here's a cross-section of that river. It's a very steep bank, the cut bank, the eroding bank, and the bottom of the river rises slowly away from the cut bank. Right here, where right up in the deepest part of the river, you have sediments which are deposited in scoured out cavities. Then you hit flat-lying strata, which will be turned into sidewalk slabs. And as you go towards the shallow side of the river, you encounter the inclined beds. So one kind of sediment, a second kind of sediment, a third kind of sediment, and a fourth type of sediment structure, depending on where you are in the river channel.
Well, those are drill marks, of course, from the
Yeah.
quarry, right?
Yeah.
And am I looking at,
Where?
well, all these vertical?
Is this a strata here?
Yes, right.
That's been
Oh, those
drilled
Yeah.
through and then broken off
To make some stone structures. So it almost looks like bricks from the end. But
Doesn't it?
it's,
Yeah.
So they must have been looking for a certain type of break.
This is the stuff Harvey Fight prized in creating those walls.
Uh-huh, okay, right.
On September 15th at 9:30 in the morning, the workers are here drilling those holes.
Yeah.
That was a long time ago.
Would there be a lot of fossil remains in a river sediment like that? I guess it depends on the time period.
You'd
of
want
course.
plant fragments, wouldn't you?
Yeah, like a lot of
Yeah.
palm,
And,
fronds or something.
Living in these rivers were clams, freshwater clams. There were worms that burrowed through the sediments. There were plant fragments carried down the river from during floods.
Yeah.
And they're so rare here, and I can't account for that.
Oh, really? Okay.
It's such a disappointment.
Mm-hmm.
I'm going to show you one fossil plant later on.
Yeah.
Well, there is a wall of rock. Oh, here's a structure. During a flood, the floodwaters scoured out this surface. Then when the floodwaters passed, these strata were deposited. Earlier in time, there had been another flood, and those sands had been deposited at that moment in time. Flood, flood, and something else. Look at this surface. It curves, it rises in that direction. It rises in that direction, and it reaches a bottom right here. What is it? A river channel. A river channel. All of this is river deposits. There was a moment in time when that was the bottom of a river. The bottom rises in that direction, sinks to there, and rises in that direction. I stand right here I'm up to my neck in river sediments. I'm looking in that direction, and the currents are coming towards me. In the minute or so I have before I drown, I am experiencing the river. I'm buried in all this sand. I'm facing into the river channel, and I'm dying of drowning. This was a moment in time when the rivers are meandering streams on deltas. They meander left to right, right to left, left to right, across the surface of the delta. This is a moment in time. It might have been the same river, it was here, but that river meandered in that direction, came back, carved this channel, kept going in that direction. If we could see the rocks above, we would say maybe the very same river coming back, meandering and back. I stand in front of you and I am touching the bottom of a river. As we come to understand the stratigraphy here, we build a bigger and deeper understanding of what this bedrock represents, what it means. The slopes are pointing a downstream direction. The flood came from there, went in that direction.
For example, here you pointed out these two. Right, the one on top is a more severe flood than the one beneath it.
Oh, I didn't say that actually. I said there were 2 episodes of flooding going on, and this could be a 3rd episode of flood. This certainly is a 3rd episode of flooding. That's what that says there.
My question is if the steeper slope would infer more water, it's more severe flood than a more shallow deposition.
No.
No.
The slope of these strata is the slope of a dune-like sandbar that is being carried by the floodwaters in a downstream direction. That sandbar does have a steep slope, but the river slope is probably less than 1%, extending all the way back to the Acadian Mountains, rising above that horizon. The floodwaters are coming from there and descending a slope which is minuscule, very low. And that slope has little influence on the speed of the river. Well, we continue on a common theme. We examine the rocks and we conjure up images from the past, a story that the rocks are telling us. Every day, I've been a professional geologist since 1974, and virtually every day of all that time has been past, making observations, asking questions, and coming up with answers of this sort. There. When we see, there are places in the quarry where you can see what was once in those cavities. What am I standing on?
Bluestone?
Bluestone is right, but it's not quite specific enough.
Like sand waves,
Sand waves, you're getting a lot closer with that.
Sedimentation.
We like to call these ripple marks. We conjure up an image of when that was the bottom of a river. I am standing at the bottom of a river, and there's a current flowing across that, sands at that bottom. They're picking up the sand, they're carrying it forward a little bit, and depositing it as ripples. There's a steep slope to each ripple and a gentle slope. The steep slope points in the direction of the flow of the water. Ripple marks are very photogenic, very appealing to the eye, and the kind of feature that once you've seen them, you may never have noticed them before, but carrying around with you your trained eyes, your newly trained eyes, you may in the future someday say, look at that. Why, those are ripple marks. The flow of the water, the speed of the flow of the water, the size of the sand grains combine to dictate the size of the ripples and to some extent the shape of the ripples. We are going to see some better ripples in a little bit. We walk to this wall where you'll be able to stand in the shade. Look at that, that's some nice striations. The bluestone quarry operators valued these fractures that we've already seen. When they're dynamiting in the quarry, the rock breaks along these fractures, and you can obtain from them shaped rock slabs that make such nice sidewalk slabs. But look at this. This is the same as this. You've already noticed the fractures of the rock. You've noticed that they're parallel to each other. There are multiple, there are so many of them, but now we have a whole different insight as to what these fractures are. They, when you've had quarrying going on, are blasted out as vertical, almost smooth walls of rock. Geologists have a word for this. They're geological joints. The rock fractures into these joints. The process is something we call jointing. So now we understand the fractures a lot better than we did up there, because we have such a better visual impression of these fractures, but we haven't explained how they originated. We've seen the pattern. They're all parallel. They're all straight and smooth. The pattern is there, the pattern is there, the pattern is there, but we're seeking to explain the pattern, and if we can come up with an explanation, it will reveal to us a very different, whole different story, perhaps something that's really important, but certainly something that is interesting. Let's talk about that. It takes us back 250 million years, 250 million years ago. And what was going on at that moment in time was really rather astonishing. I'm old enough to remember the years just before plate tectonics. When I was a young man, the issue of plate tectonics was entirely unknown. I was brought up in teaching undergraduate, or not teaching, but taking undergraduate courses where nobody knew about plate tectonics. Nobody knew how mountains formed. I remember sitting in my geomorphology class, and the professor got to the issue of mountains, and he could describe different types of mountains, old mountains, young mountains. But when it came to trying to explain how mountains formed, there was a pained look on his face because he didn't know. But he was a senior full professor, Dr. Sir, and had to know everything, didn't he? So he conjured up an image of how mountains formed. He talked about the crust going down and then rebounding, going back up. And during the going up process, they crinkled, they folded into mountains. I forget the name of this hypothesis. The crust went down as far as it could, came up above where it started, and there were the mountains.
Sort of like baking a pie.
It sounded good, and if you could explain it, if you could tug upon your white beard and make the explanation, you could sell it to people. And I think everybody in the room thought, this is, but they don't know. He doesn't. Professor Wolf does not know how mountains formed, and neither do I. But I lived to see plate tectonics appear and to understand its implications, which were truly profound. I was able to witness on the ground a tremendous scientific revolution. It was as if I'd lived in 1859 and caught wind of Charles Darwin's theory of evolution. It was as if I lived in the 1790s and I was there when James Hutton first came to understand approximately how old the Earth was. Hundreds of millions of years, he thought. He was only wrong by about 10. They're several billion years old. The story begins a quarter of a billion years ago, when in that direction, Africa is approaching North America. One continent is approaching the other, and there's going to be a collision.
But why?
A collision.
But why? Why is it approaching it?
Oh,
Sorry.
it's being driven by a mid-oceanic ridge way beyond it. Great masses of hot, billowing, molten rock are rising to the surface and then pushing sideways. Seafloor spreading, which pushes ahead of it continents. So, somewhere on the other side of North America, a seafloor ridge is pushing North America that way, and somewhere Africa is being pushed this way, and the two continents are colliding. It wasn't that quick, but it was that exciting. It was two continents colliding with each other. Huh. How did it was tough. This was a tough sell in the late 1960s, but the evidence was there. What happens when two continents collide is the rocks are compressed, and rocks are pretty good at that. They don't mind being compressed. If you're compressed by North America on one side, Africa on the other, you're going to be squished. You're going to have a last moment and you're going to die. But rocks do pretty well. They don't seem to mind it whatsoever. They handle the compression. They handle it. The great mountain building event occurs. The great collision occurs. The rocks sit there for a couple tens of millions of years. And then Africa backed away. Africa began drifting off to what we call the Southwest today. And that's where the rocks got into trouble. They did not mind being compressed, but they became very unstable when they were separating, when the compression was being reduced. The rocks reacted to this loss of compression by fracturing. It was a moment in time, a split second, when these joints occurred. A very loud cracking sound, but no motion. This was not an earthquake. An earthquake is an entirely different shaking of the planet. This was not. This was decompression. This was splitting of the rocks. And the decompression was in that direction, in that direction. The fractures are oriented as you see. What an astonishing thing. We look at a crack in the rock, we look at a wall, a cliff, flat as can be, and we conjure up the image of Africa colliding with North America. You see what I said? We see a pattern, and we want to solve what accounts for that pattern in the hopes that it will reveal to us something important, a scientific discovery. One of the great discoveries of my lifetime, of my career.
But why did Africa back away?
Down beneath, we can see what's going on today. Was it the Red Sea between Saudi Arabia and Africa? Witnesses a seafloor ridge beneath the surface. Great masses of molten rock are rising toward the surface, splitting Saudi Arabia away from Africa, and there certainly are beneath the surface fractures of this sort. Come back in 50 million years, and Saudi Arabia and Africa will be separated by many, many more miles than they are today. And that's what apparently happened here. Yeah.
So these fractures are only found where those continents are coming together?
No, there are other ways of forming joints, but this is what happened right here. Now, I want to give you a vivid image of the moment when this split, this fracture occurred. We're going to go over here. The fractures extended once into the air, Who knows?
Yeah, oh, I see, right. of
And it
course.
extends into the ground. Who knows?
Yeah,
I've never been there.
right.
This, you now have a trained eye, and you will recognize as a joint surface, a parallel joint surface to the one across the quarry from me. But there's something else here. Look at that. Yeah. Now, I'm not going to ask you to explain that. There's really no way you should be able to. But we call this a plumose structure. The word plumose refers to a bird feather. And you'll see how much this resembles a bird feather, the center axis of the feather, and patterns extending down and radiating up. It looks as if some gigantic feathered dinosaur died here and left this gigantic feather fossil behind. But it's not. It's not a petrified feather. It's a plumose structure. It records the moment of that jointing. The fracture began about here and radiated in that direction, and the fracturing created that structure. In your mind's ear, generate that great cracking sound, and at the speed of sound, I'm told, the fracture radiated through the rock. It's a graphic visual image of the jointing process. It's an image of an instantaneous fracture of the rocks. Isn't that wonderful? Yeah. Now, again,
That doesn't explain why that pattern.
oh,
At least to
boy,
me,
you
it doesn't.
ask tough questions. Well, the conjugated radiating fissure is represented in that pattern.
So it's start and then progression out.
Goes in that direction at the speed of sound. When you fracture glass, you get something called a conchoidal fracture. Do you know what the fracture of glass looks like? Yeah, that's called the conchoidal structure. And it's the pattern of fracture within glass. Well, this is the pattern of fracture within rock, within sandstone. Now, that sounds as if I answered your question, but of course I didn't. And which betrays the fact that, no, I can't explain why it has that pattern. I can't not answer.
So different materials have their own unique pattern?
Yes.
That's interesting.
Flint, which Indians used to turn into arrowheads, displays a conchoidal fracture, and that is how a tool-making Stone Age person could chip away at flint and shape it. He could hit the rock, the flint, and he knew how the pattern would occur, and he could control the shape of the arrowhead or the hand axe because he understood the fracture pattern of flint. Again, today, you're one place after another, you're developing your trained eyes. And I want you, for the rest of your lives, wherever you go, when you see bedrock, I want you to start watching for these patterns. This is something you won't see very often, but you will be able to see it from time to time. And imagine how smart you'll look when you walk up to the rock and point at it and tell the tale that I just told. You'll look
Okay, so
educated.
What's the deal with the colors?
The color, well, that I can answer. The yellow and the orange and the brown are combinations of oxygen, hydrogen, and iron in a mineral that we call limonite. And depending on how much oxygen is in it, the limonite is yellow or brown or orange. And so the composition varies. But the color is the color of the mineral that is in the rock. The mineral is a product of chemical weathering, a process very similar to what we call rust. If you combine water, H2O, with iron, it will rust and turn into limonite. The yellow stuff we call rust is limonite. We're going to see a remarkable, another remarkable structure. Well, you bring to this location your newly trained eyes, and you look down and you see ripples. Nice, that was quick. Which way was the water going? Okay, we're standing on the floor of a river, and the river was flowing in that direction, and it produced a remarkably good surface of rippled sediments. You're going to have a hard time forgetting the imagery that is presented to us here. And it's imagery I hope you will carry around with you for the rest of your life. And I hope that several times in the future, you'll spot these things on your own. And you've learned something on our trip. You've learned a little science. And you'll be able to stand and point and wave your arms and speak of the currents that once flowed in that direction. It is a wonderful thing to carry around with you and to have with you when you're looking at rocks. What should be more dull than rocks? And yet there's so many stories I can conjure up wandering around this location. And they're interesting stories, at least I think so. Somebody asked what made the bubbles or the holes, the cavities in the sandstone, and here they are. Here are two empty ones, and here are two filled ones. These are balls of clay. Somewhere upstream there was a bank composed of clay, real good, the kind of clay you used to buy in a hardware store and use to do modeling. The river cut into that bank and eroded out masses of clay. They broke up and they rolled downstream, carried by the currents. And they rolled up into almost circular, very round structures. And on the surface of these is a coating of sand. So this was an interesting problem. My wife and I spotted these cavities 20 years ago, and we were perplexed. We could not explain them. As all we had to look at were cavities. We didn't have the evidence. But on a trip here, we spotted, I think it was this very rock, and we saw and understood that the cavities had once been filled with clay, and that rock clay has turned into petrified clay. And where it pops out, you're left with cavities. Where it is not popped out, you're left with explanations for the question. So there you go. I deferred answering that question, but I did indeed get around to it.
I can't remember the question.
Come as close as you can. Yep. Well, here we have another one of those patterns. Dot, 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 all lined up. What a curious thing.
It's a wordle game. It's connections.
It is a fossil tree. It is the trunk of a tree. It's the kind of tree which has leaves which would remind you of spikes. They're skinny, they're cylindrical, they come to a point, they radiate out from the trunk of the tree. Well, it might have grown in the swamp. I'd like to put it on the bank of the river.
Right.
Go up to the upper bank where the soil is wet, but not too wet. And you can have this tree growth. This is the best fossil I can show anyone in the whole quarry. What a disappointment.
Why?
Yeah, it's the only one I know of. This is called the lycopod tree, and there's not likely you've seen anything alive today which would be a lycopod, except maybe you're familiar with something called the ground pine. No.
They're very small.
Yeah, the ground pine is not a tree. It's a very small plant and is a lycopod plant. These are Devonian-aged plants. They're quite primitive, and in no way do they resemble a broadleaf tree or a pine tree. The conifers and the broadleaf trees had no matches in the Devonian. Nobody has ever found a conifer. Nobody has ever found a broadleaf flowering plant in the Devonian. They had not yet evolved.
So remind us, when was the Devonian?
Oh, it began 419 million years ago, and it came to an end 359 million years ago. 68 million years is represented during the Devonian time period, and that was the pinnacle of plant evolution at that time. Well, no, there's no specific reason that brings a time period to an end. The Devonian did come to an end with a massive extinction, so that the fossil record at the very close of the Devonian does not really closely resemble the fossil record at the beginning of the next period of time, which is called the Mississippian. There can be great biological events which define the end of a time period, or there could be a great physical event. The breakup of the continent of Pangaea comes at the end of the Permian time period and accounts for dramatic events that you see in the stratigraphy of that time. The disappearance of the dinosaurs at the close of the Cretaceous defines the end of that time period. There are strata with dinosaurs, and then they stop. At the end of the Permian time period, the trilobites instantaneously disappear. So those are two biological events. I'm going to call this an oration, and kind of a summation of what's represented in the geological history of the Opus 40 quarry. We're going to go back in time those 385 million years, and we are the mind's eye, the human imagination. We can go anywhere, we can do anything, we can rise into the sky, we can drop into the ocean. We're the human imagination, the mind's eye. Currently, we're a mile up into the air, 385 million years ago, and we're above the town of Oneonta, what is now the western Catskill Mountains. And we are drifting through the sky, heading towards the east. Down below us is the Catskill Sea. That's the ocean that's spread out west of the rising mountains of the Acadians. That's the ocean that is spread out west of the Catskill Delta. We're drifting through the sky, heading east and looking down. And it's a dark blue ocean down there beneath us. And it's a still ocean. There are no white caps, there are no waves that we can see. It's a quiet ocean. We continue drifting to the east, but beneath us the planet is spinning to the west. It's revolving. So we're going east, and the ocean beneath us is going west. We continue, and we're convinced that the waters are becoming a lighter tint of blue, and we're deducing that the waters are becoming shallow, or more shallow, and we're guessing that we are approaching a shoreline, one that we can't see yet, but we think is out there, and that we're heading towards it. We continue east, the ground beneath us goes west, we go east, it goes west, and there, on the distant horizon, is a glimmer of white, and we go east, it comes west, and it rises above the horizon, and when it gets high enough, we see that it's a triangle, and it's joined by another up in that direction, and another in that direction, and then a third, and a fourth, and a fifth. and they keep rising above the horizon until we recognize that these are the peaks of the Acadian Mountains. They rise to points, to pyramids. The whiteness becomes brighter, shinier, the sun is shining down, and what we determine is snow and ice. We go east, they come west, we go east, they come west. We see the horizontal line at the bottom, which we call the snow line. And we reach, we can see the snow line. Below that are the slopes of the mountains, which are a gunmetal blue. They're cut by the darkness of canyons, of ravines. We go east, it comes west, we go east, it comes west. The gunmetal blue is followed by a red. And then as we go east, we see a green. We're approaching the Acadian Mountains, and now we're seeing the green of the Catskill Delta. We drop down to 3,000 feet, to 1,000 feet, and even though we're lower, we start to see the coastline. We see the beaches of the Catskill Delta. These are not the white quartz sands that you're used to here in eastern North America. They're dirty, they're brown, they're red. These are the sediments that have washed out of the Acadian Mountains, been carried across the Catskill Delta. Now we can look down and we can see distributaries, rivers flowing across the delta, one distributary after another. And many of them are quite big. These are big rivers. The one that we just visited was a sizable river to accumulate all of that sediment. It had to be. We go east, we drop down, we go east, we drop down, and we spot a very sizable distributary stream where it empties into the Catskill Sea. We hone in on it, we drop down to 50 feet, to 20 feet, and then we pass across the coastline and we follow that river channel in an upstream direction. The first scientific discovery we make is that there has been, in recent weeks and perhaps months, a drought. There is a river of sorts. It's not a continuous flowing river. It's a series of pools lying at the bottom of the river channel. We drop down to 3 feet above the nearest pool, and we hang in the air and we look down. And then we go up the side of the pool on one side, get to the end and come down on the other side at the other edge of the pool. And there we see fish swimming in that pool. And these are unhappy looking fish. They've been suffering. Oh, it's easy for you to laugh. Yeah, you don't care about these fish. Yeah. These fish have been struggling to overcome the effects of the drought. The waters have been warming up in the tropical sun, and the waters have been losing their oxygen content. The fish are dying of heat, and they're dying from an absence of oxygen. They're struggling up the stream, they're struggling down the stream. They're hoping to find cooler waters with a lot more oxygen in them. This is not going to happen. These are very unhappy looking fish. Out in the middle of the pool, we see other things. We see clams. They're about 3 inches long and about 3/4 of an inch wide. 2 big valves clustered together, and they're facing in a downstream direction, rising up out of the sediment, wide open shells. Under normal circumstances, they face into the current and they feed on particles of biological material that have been brought to them by the currents of the stream. But there are no currents to the stream today, no currents in a drought. The clams are wide apart, hoping a current will bring them food. It's been weeks since that has happened. These clams are dying of hunger, and they're struggling. You gonna laugh at that one too? Yeah, poor dying clams, empty bellies dying of hunger, and you don't care. Yeah, you don't care.
I care about the fish.
Yeah, oh, you didn't, you laughed at them.
I laughed because you said unhappy looking.
We continue, we get up in the air and we continue inland and along the bottom of this channel. And rising up above us, we start to see trees. And there's those lycopod trees I spoke of before. They have those strange trunks with bristling, spiky leaves radiating out from them. There's a foliage of sort at the top, something that was more like leaves, but these are bizarre trees. We gaze up into this forest. It's one of the oldest forests in the face of the planet Earth. The concept of the forest had only recently evolved, and we're looking at some of the oldest forests that have ever been in our planet's history. Not like this one here today. We drop down close to the ground and we go exploring. There are things that we would call weeds down there, but they don't look at all like the weeds we see today. But then we see something that is finally familiar. It is a centipede, an animal which is common today. A centipede is supposed to have 100 segments, and on each of those segments there's supposed to be a pair of legs. And when I was a kid, we used to see them all the time. To this day, we find them on our porch. Somehow, if you leave a bucket out on the porch and you lift the bucket, there's almost always a centipede under it. I don't know how it gets in there, but you've all seen centipedes. You know of what I speak. The next time you see a centipede, I'd like you to kneel down and look very carefully at it. And you're going to say, because you went on this trip, that looks like a Devonian-aged primitive animal. That's exactly what it is. The centipedes have hardly evolved at all in all of those hundreds of millions of years. And we call them living fossils. We call them animals that just have not evolved. Our ancestors did a lot better than their ancestors did. Then we see a thousand-legger, a myriapod, a very similar segmented animal with more legs. And then we see a spider. And then we see a scorpion. And at last we're looking at animals that do share the planet with us today, but each of them is a living fossil. I'd like you to look at that centipede the next chance you get. Look at the millipede the next chance you get. And to appreciate how primitive a spider is, or a scorpion for that matter. When you look at these animals, you're gazing into the Devonian age past. You're looking at living fossils. It's a wonderful thing. You now...
They were bigger in scale, excuse me for interrupting, but weren't some of those things like 2 feet long?
Yeah, there were millipedes, relatives, that were 6 feet long. Yeah, think about that. Look at a centipede and think of one a foot long and contemplate that. No thanks. No thanks. I don't want to deal with that animal. Well, we have been looking at the Devonian age. There are no amphibians, there are no reptiles, there are no birds, there's certainly no mammals living in the Catskill Delta. There are the plants and animals that dwelled upon our planet, that had evolved on our planet by the time of the Devonian. And we're so lucky to have their fossils to know what it was like at that time. We continue up the river. There's no name to the river. They didn't name rivers back then. We pick up speed and we're heading inland. The Acadian mountain range is rising above us as closer we get to it. And we're appreciating that it's a gigantic range of mountains. And we're picking up speed and we're going inland, and the banks start to rise above us. And the banks are composed of coarse sand and gravel. We're getting close to the Acadian Mountains, and this is the stuff that has weathered out of those mountains and been deposited at the base of those mountains. We come to a screeching halt and we look up the slopes of the Acadians and are awed. You could do this today by traveling to Nepal, north of Bangladesh, and gaze up the slopes of the Himalaya Mountains. you could see the sight that we, the mind's eye, are envisioning right now at this moment. The world today has analogs to the world of the past. Well, we're determined to go up there, and we start up. We pick the biggest canyon we can find. We rise up that canyon 1,000 feet, 2,000 feet, 3,000 feet, and that's where the foliage ends. Plants have not yet evolved an ability to live at higher elevations, and we don't see them anymore. Below us are mosses, our lichens, our algae, and a host of primitive plants, including things that you would call trees. We continue up the slopes of the Acadian Mountains, rising higher and higher. Suddenly we pass the snow line. Suddenly we stop and look all around us, and it's all ice and it's all snow. We continue up until we get to the very peak, the tippy top of the nearest mountain, and we stand there at the peak. What is Everest? I think 28,000 feet. We get out our cell phone and look at the altimeter, and we find we're at 27,932 feet. We've been robbed. We're not as tall as Mount Everest. But where we are, at the top of the Himalayas, we look to the south and there's peak after peak after peak. We look to the north and there's peak after peak after peak. It's a big mountain range, and we're privileged to stand atop that mountain range. Wow. And we spend 10 minutes there. Why is that? People today, they book passage to the Himalayas, they reserve hotel rooms, they reserve planes to get there. They travel up to base camp number 1, they spend a couple of nights. They go to base camp number 2, spend a couple of nights, base camp 3, base camp 4. And then they get to the peak, they spend 10 minutes, they take a few pictures, and they head back. What kind of logic is that? We're bringing tanks of oxygen here. We can do it. We can do it. Yeah.
They got to get to the next
He's got
bucket
the
list
stuff.
item.
Yeah. Got to go to the next place. Got to go home and go into a bar and brag about how you climbed Everest, I think is what actually happens. We pick up speed. We're going down. But then we pause and stop. And there in front of us, we forgot, it's the Catskill Delta. It's green. It's spread out for a few hundred miles off to the west. And then we look, and crossing the coastline is a line of thunderstorms. There's been a drought, remember? The drought is going to come to an end. What happens is that at the end of the summer, the delta heats up so much that the hot air starts rising. And as it rises, it draws cooler air off of the ocean to replace it. The cool air passes across the delta, it cools down, and turns into a line of thunderstorms. Not one, but that first line is followed by the second line of thunderstorms, and then a third line of thunderstorms. And we go, uh-oh, we're going to have a lot more trouble going back than we had coming up. But persevere we do. Down the slopes we go. 50 miles, 60 miles, 80 miles an hour, 100 miles an hour down the slopes of the Acadian Mountains. The mind's eye can do this. We're so lucky to have the mind's eye. Out onto the flats of the Catskill Delta, and before you know it, slam bang into the first line of thunderstorms. The lightning flashes, the wind blows. Bum 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 bum. We struggle through the raging winds. The rain pounds down upon us, but on we go. We go west, it goes east. We go west, it goes east. And we leave the first line of thunderstorms. Da 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 da. The sun comes out. the wind dies down, and we look about us, and there's water in the stream channels, and the soils all around us are wet from that strong storm. We go west, the second line of storms goes east. We go west, it goes east. And sure enough, slam, into it we go. The winds howl, the lightning is flashing, the thunder is pounding. We can hear the branches of the trees splintering in the wind. We can feel now the power of a thunderstorm which is worse than the last one. We go west, it goes east. We go west, it goes east. And da-da, out we come. The sun comes out again. But now we pause, we turn 360 degrees, and there's a mess out there. There are pools of water where there had been a drought only hours ago. The water is soggy. There are trees standing there with broken limbs, with fractured branches. The ground is littered with the debris of foliage. We go west, it goes east. The third line of storms is going east. We go west. Is there anybody here who doesn't think this won't be the worst of the three? No, nobody's raising their hand. Of course it's going to be the worst of these three. Into it we go. The wind roars, rages, pounds. It blows our hair around. It blows us back and forth. We can hear the lightning crash. Flashes of light worse than we've ever seen before in all of our lives. This is a line of thunderstorms. This is a horrible line of thunderstorms, and we, the mind's eye, have nothing to fear. Nothing can damage the mind's eye. Nothing whatsoever. So we hang out. We let the storm rage. The sounds of breaking, not splintering, but breaking trees, which we can't see. The water, the rainwater is so dense that we cannot see anything that's going on. We can feel it, we can hear it, but we really can't see it. West we go, east it goes. We come out at the end of the third line of storms. Then the sun comes out, the winds die out, and it is a god-awful mess. All of the trees have been blown down. All of them have been splintered and broken and brought to the ground by the storm that has just passed. We continue to the west a little bit, then we pause, we turn around and we look east, and we hang up in the air above the stream channel. The very same stream that we followed on our way in just an hour ago. And we look down and we see it starting to fill with water. The fish look happy. Can a fish smile? Well, our fish would smile if they could. The temperature of the water has dropped. The oxygen content has dropped. The clams look good. There are currents. The currents are bringing them food. They open their valves and they suck in water that has vegetation in it, has food within it. Clams, if they can look happy, are looking happy. We hang out in the air, and then we notice that the water of that river channel is rising and rising and rising. And the power of the flow is picking up. We can only guess, but we're sure we're right. Ripples are being formed at the bottom of that stream, right beneath us. We can't see that, but we know it's going on. We know that that stream is carrying enormous amounts of sand. We can not see into the river waters. They're cloudy with sediment, sand and silt and clay. And we hang in the air and we watch this happen. The river waters rise to the top of the bank, and then the flood spreads out across the delta, meeting the waters from the next distributary, meeting the waters from the next distributary. We rise up 1,000 feet higher and we look down, and we turn those 360 degrees once again, and we see the whole delta is underwater. It's not raging, it's not foaming, it's not powerful. It's a funny thing about floods. Once they spread out across the floodplain or the delta, the waters slow down and settle down and don't look dramatic and don't look violent. We hang in the air 1,000 feet high into the sky, and we gaze down at the devastation below it. It's getting late in the afternoon. It's 4 o'clock. It's 5 o'clock. The power of the rivers is picking up. The fish are struggling. These fish are primitive. They're not very good swimmers. They have poor fins, poor tails. The power of the flow is slowing them down. The power of the flow is weakening them. These fish are struggling. These fish who were so happy to see the floodwaters come are looking at their watches and wondering, how long will it be that I can hold up under these? You don't care at all.
I care. I love their
Don't.
watches.
You don't.
I
You're a
love the
cruel
fishy
person.
watches.
You're a cruel person. The fish are slowing down. The fish are struggling. They're weakening. They're running out of oxygen. They're slowing down some more. They come to a halt. They slowly turn over and they rise towards the surface, belly up, to become part of the flotsam of the flood. The clams are doing better. The clams have been pretty happy at the end of the flood, but now they're being swept up in the moving sediment. They're being carried by the currents in the sediment. They're being carried to the west down the stream. They don't struggle. They can't struggle. They can close up their valves and bounce along with the power of the flow. They are nervous. They don't like anything that's happening to them, and they don't know what their chances are either. We're the mind's eye. It's 6 o'clock. It's 7 o'clock. It's 10 o'clock at night, and we gaze to the east. It's dark out, but at about 10:30, we start to see a glow of light on the horizon. It's a rising full moon. At exactly, we turn around and we look back on the Catskill Delta after this long day of devastation. We expect to see red lights going on and off. We expect to hear voices being magnified by electronic devices. We expect to see down there the Red Cross passing out donuts and coffee to rescue workers. But there are no rescue workers down there. There are no rescuing going on down there. No one down there who's still alive is doing anything but struggling to stay alive. And few of them are succeeding in doing that. It gets later and later, and the creatures down there are dying one after another, and there's nobody there to help. At exactly 11:59, the moon rises above the peak of the Acadian Mountains, and the moonlight radiates down onto the devastated Catskill Delta. We hang in the air. We turn those 360 degrees. Still, one more time, we have been privileged to see the origin of that. That's where this stuff came from. That's where those sediments came from. Only the hardening was needed to produce the quarry that Harvey Fight worked. Oh, I wish Harvey could come along on one of these trips and get an insight as to what had gone on here ahead of him. At exactly midnight, bong, 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 the moonlight radiates across the whole delta, and down there in the nearest stream. Having been buried under 3 feet of sediment, the first of the clams has worked its way to the surface. It faces upstream, it opens up its valves, it gets its best meal in 2 months. Life goes on.
Thank you.